We're going to explore the world of heavy ion fusion.
Okay.
Smashing atoms together to create totally new elements.
Yeah.
We'll be diving deep into a recent scientific paper that's making some, big waves in the field.
Wow.
It's titled Demystifying the Fusion Mechanism in Heavy Ion Collisions, a six-dimensional Langevin dissipative dynamics approach.
Sounds pretty complicated.
It does a little bit.
But trust me, it's really fascinating stuff.
Okay.
This paper is really presenting a new way to model these atomic collisions, and it could revolutionize how we understand how super heavy elements are created.
Okay, I have to admit the title alone makes my head spin a little.
Yeah.
But before we get lost in six dimensions,
Okay.
can we just back up for a second, talk about the basics?
Sure.
What exactly is heavy ion fusion and why should we care?
Well, imagine you're trying to fuse two tiny magnets together.
Okay.
When they both have the same charge and they want to push each other apart.
Yeah.
That's essentially what heavy ion fusion is like.
Okay.
You're taking the nuclei of two atoms and forcing them to combine, overcoming their natural repulsion. And if you get it just right, they'll fuse to form a brand new, heavier element.
So it's like atomic Legos.
That's a great way to think about it.
Building bigger and bigger elements by smashing smaller ones together.
Yeah, exactly. And this process, heavy ion fusion, is how scientists create those really elusive super heavy elements.
Oh.
The ones beyond element 118 on the periodic table.
Wow.
These elements don't exist naturally, so we have to get creative and make them ourselves.
So I'm starting to see why this is such a big deal.
Yeah.
It's like we're rewriting the periodic table in real time. But I can imagine it's not as simple as just smashing any two atoms together, right?
You're absolutely right. There's a whole lot more to it than that. You have to get the energy just right. Consider the shapes of the nuclei, how they're rotating.
Wow.
It's a very delicate dance.
Yeah.
And predicting whether fusion will occur is incredibly complex, and that's where these mathematical models come in.
So this paper we're diving into with this super long title,
Right.
It's basically presenting a new and improved model for predicting heavy ion fusion.
Exactly. It's called the six-dimensional Langevin framework.
Okay.
And it's a major step forward in the field.
Okay.
Think of it like this. Imagine you're trying to predict the path of a dust particle in a room full of kids running around kicking up dust.
Oh, yeah.
It's chaotic, right?
Oh, tell me about it.
Yeah.
My house is basically a giant dust particle experiment.
Right. So to predict the movement of that dust particle, you have to take into account all the random forces acting on it, the air currents, collisions with other particles, and so on.
Wow.
The Langevin equation is a mathematical tool that helps us model these kinds of chaotic systems.
So they're applying the same idea to heavy ion fusion, because those atomic collisions are pretty chaotic too, I imagine.
Precisely, the six-dimensional part.
Yeah.
Refers to the fact that this model tracks 6 different variables that affect the colliding ions. 3 for their shapes and 3 for their rotation.
Oh, wow.
It's way more detailed than previous models.
So that makes it...
Which makes it much more accurate at predicting the outcome of these collisions.
Okay. I'm starting to wrap my head around the concept.
Good.
But what makes this model so special? What sets it apart from previous attempts to model these collisions?
One of the key things about this new model is how it handles something called the asymmetry parameter.
Okay.
This basically measures how evenly the mass is distributed between the two colliding ions.
Okay.
You see, in previous models, this parameter was quite restricted. But this new six-dimensional framework allows for much more freedom.
So it's more flexible.
Yeah, you got it.
And that lets it capture the real-world messiness of these collisions.
Exactly. It's like upgrading from a basic calculator to a supercomputer.
Nice.
You can do so much more, and the results are far more precise.
All right, I'm sold. This new model sounds pretty impressive.
Yeah.
But let's unpack how it actually works.
Okay.
The paper describes the fusion process happening in stages, right? Can we walk through those?
Absolutely. Think of it like a 3-act play.
Okay, I like it.
In the first act, we have the initial deceleration phase.
Okay.
This is where the ions are approaching each other but still feeling each other out. Remember, they're both positively charged.
Yeah.
So they're naturally repelling each other.
So it's a slow and cautious approach.
Exactly.
Like they're sizing each other up before making a move.
Exactly. But as they get closer, their speed decreases because of this electrostatic repulsion.
Okay.
What's fascinating is that the model suggests they don't really change shape that much during the stage.
Oh.
They stay fairly spherical until things get really close.
Okay, so it's a tense standoff.
Yeah.
Then what happens?
Then we move into the second act, the contact phase.
Oh.
Where things get really exciting.
Okay.
Once the ions get close enough for their nuclear forces to kick in, they suddenly snap together.
Oh, wow.
The paper calls this almost instantaneous neck formation.
Wait, hold on. They go from repelling each other to basically merging.
Yeah.
In a split second, that sounds kind of dramatic even for the atomic world.
It is, and this is a crucial point that the model highlights.
Okay.
It all comes down to the strong attraction between the nucleons, those particles that make up the nucleus.
Right.
When the edges of the nuclei overlap enough, the nuclear forces take over.
Okay.
And they rapidly rearrange themselves to create this neck between the two ions.
So it's like a sudden, irresistible attraction.
Precisely.
They can't resist each other anymore.
Precisely, and this happens incredibly fast.
Wow.
Because the nucleonic densities, basically how tightly packed the particles are, want to be uniform.
Okay.
So they snap together to create a smooth, consistent density throughout the newly formed structure.
I'm picturing like 2 drops of water merging together.
Yeah.
Except way faster.
Yeah.
And on a much smaller scale.
That's a great analogy, but the story isn't over yet.
Oh.
The third act is where things get really interesting.
Oh, what happens in this final act?
Well,
do they live happily ever after?
Not so fast.
Okay.
This stage is called creeping motion.
Okay.
And it's basically a tug of war between the nuclear forces trying to hold the newly merged nuclei together.
Right.
And the Coulomb forces trying to tear them apart.
So it's a battle of epic proportions,
Exactly.
but on a microscopic scale.
Exactly. And the outcome of this battle determines whether we get a new element.
Oh, wow.
Or the ions just separate again. It all depends on the energy of the collision, the shapes of the nuclei, how they're rotating, and a whole bunch of other factors.
This is where I'm really glad we have these sophisticated models.
Yeah.
Because I can't even imagine trying to keep track of all that. So this Langevin equation, it helps us understand this complex interplay of forces in this final crucial stage.
Yes, it's a powerful tool for modeling this delicate dance between attraction and repulsion.
Okay.
It takes into account all the randomness and friction involved and helps us predict whether fusion will occur or not.
This is truly fascinating stuff. Yeah. And I'm eager to learn more about how this model actually performed in like real-world tests.
Okay.
But I think that's a story for part 2 of our deep dive.
Right.
Join us then as we explore the exciting results of this groundbreaking research.
Welcome back to the deep dive. We're picking up right where we left off with our exploration of heavy ion fusion.
Yeah.
This, incredible new model that's helping scientists simulate these mind-blowing atomic collisions.
Yeah, we've covered the basics of heavy ion fusion and how this 6-dimensional Langevin framework is shaking things up. But now, let's dive into the really exciting part.
Yeah, okay.
Did this model actually work? Yeah, I'm dying to know, can it actually predict what happens when you smash these atoms together?
Yeah.
Because if it can, that's huge.
Well, you're in for a treat because the researchers put this model to the test, and the results are pretty impressive.
Okay.
They focused on 2 specific collisions, both involving a nickel-64 nucleus slamming into a zirconium nucleus.
So same projectile, different targets.
Exactly. In one case, they use zirconium-92.
Okay.
And in the other, they use zirconium-96.
Okay.
Which has a few extra neutrons.
Okay.
Think of it like throwing a baseball at 2 different types of clay. One a bit harder than the other. You'd expect to see some differences in how the clay deforms, right?
Makes sense. So what happened? Did the model accurately predict the outcomes of these collisions?
For the nickel-64 and zirconium-92 collision, the model's predictions were spot on.
Wow.
It correctly predicted how fast the newly formed nucleus would spin.
Okay.
Something called the spin distribution. And it also nailed the likelihood of fusion happening at different energies.
Okay.
Which is called the fusion cross-section.
Wow, that's incredible. It's like this model can actually see into the subatomic world.
Yeah.
And tell us what's going to happen. What about the other collision with the heavier zirconium-96?
That one was a bit trickier.
Oh.
There were some slight discrepancies between the model's predictions and the experimental data.
Oh, so the model wasn't perfect. What went wrong?
Well, remember how we talked about the model assuming the nuclei are perfectly spherical?
Right, yeah.
The researchers think that assumption might have caused the discrepancy in this case.
So those extra neutrons in the heavier zirconium-96 might be throwing things off, like maybe they're causing the nucleus to be a bit more, I don't know, oblong.
You got it. It's like expecting a football to behave exactly like a baseball when you throw it.
Right.
The shape matters.
Yeah.
And those extra neutrons in zirconium-96 could be causing some subtle deformations that the model doesn't account for, at least not yet.
So it's back to the drawing board. Tweak the model a bit.
Not quite back to the drawing board, but definitely room for refinement.
Okay.
The researchers are already working on ways to incorporate these shell effects, which are quantum mechanical phenomena that can influence the shape and stability of nuclei.
Okay, so quantum mechanics, that sounds complicated.
Yeah.
Can we break that down a bit?
Yeah.
What are these shell effects and why are they important?
Think of it like this. You know how electrons in an atom occupy different energy levels or shells?
Right. Yeah.
Well, the protons and neutrons in the nucleus do something similar.
Okay.
They also have preferred energy levels. And when a nucleus has a full shell of protons or neutrons, it's particularly stable.
Okay.
Like a perfectly organized bookshelf, everything is in its place.
I'm starting to see where this is going.
Yeah.
So if a nucleus has extra neutrons, like our friend zirconium-96, those extra particles might be messing with the perfect order, making the nucleus less stable and maybe even changing its shape.
Exactly. It's like trying to squeeze one more book onto an already full shelf. It throws everything off balance.
Yeah.
These shell effects are subtle but important, especially at lower energies.
Right.
And the researchers believe incorporating them into the model will make it even more accurate.
So this model is already making waves with its ability to predict these incredibly complex collisions.
Yeah.
And now they're refining it to be even more precise. That's pretty amazing.
It's a testament to the ingenuity of scientists, isn't it?
Yeah.
They're constantly pushing the boundaries of what we know and how we understand the universe, but this is just the beginning. They have even more ambitious plans for this model.
Oh, do tell. What else are they hoping to accomplish with this six-dimensional Langevin wonder?
Well, one of the things they're exploring is adding different types of noise to the model.
Noise like static on a radio.
Not that kind of noise.
Oh.
Remember, the Langevin equation is all about modeling systems with randomness and friction. And while the current model does a great job of capturing a lot of that chaos, there's always room for improvement.
So they're trying to simulate even more of the real-world messiness that happens during these collisions.
Exactly. By incorporating more complex forms of noise, they can potentially capture things like memory effects, where past interactions influence future behavior.
Wait, hold on. You're saying these nuclei have memory?
It's not memory in the way we think of it, but rather a way of acknowledging that these nuclei aren't just reacting to the current conditions, but also carrying the baggage of their previous encounters. It's like acknowledging that every interaction leaves a trace, no matter how small.
That's incredible.
Yeah.
So they're essentially giving these nuclei a history, a story, recognizing that their past shapes their present.
It's a fascinating way to think about it, isn't it?
Yeah.
And by adding this extra layer of complexity to the model, they hope to gain even deeper insights into the dynamics of these collisions.
Okay, so this model is already impressive.
Yeah.
But it sounds like it's about to get a whole lot more powerful. But what does this all mean for our understanding of the universe?
Right.
Why should we care about these tiny atomic collisions and the models that predict them?
That's the question. Isn't it? Join us in part 3?
Okay.
As we explore the wider implications of this groundbreaking research and delve into the exciting possibilities it unlocks.
Welcome back to the deep dive. We've spent the last 2 parts, unpacking this incredible new model that's shaking up the world of heavy ion fusion.
It's been quite a journey.
It has. We've talked about smashing atoms together, creating new elements, and the mind-blowing physics behind it all.
Yeah, but, as with any scientific breakthrough, it's not just about the how, it's also about the why.
Right. Why does this research matter?
Exactly.
What doors does it open for our understanding of the universe?
Exactly.
That's a great point. So far, we've focused on the nuts and bolts of the model itself, like how it works, how accurate it is. But now I'm really curious about the bigger picture. What are the implications of this research?
Well, for starters, think about the periodic table.
Yeah.
It's not just a chart on a classroom wall. It's like a roadmap to the building blocks of the universe.
Yeah.
And with heavy ion fusion, we're essentially adding new destinations to that map.
Oh,
We're creating elements that have never existed before.
That's amazing.
And that's incredibly exciting.
Yeah, it's like we're explorers charting uncharted territory.
Exactly.
Who knows what we might find in these new regions of the periodic table?
Right.
What kind of properties might these super heavy elements have?
That's the million-dollar question. They could have properties that we can't even imagine right now.
Wow.
Properties that could revolutionize fields like materials, science, medicine, energy production, you name it.
Wow.
Imagine materials that are lighter and stronger than anything we have today.
Yeah.
Or medical isotopes that target diseases with incredible precision.
That would be incredible. It's mind-boggling to think about the possibilities.
It really is.
We could be on the cusp of like a technological revolution, all thanks to these tiny atomic collisions.
It's true.
But beyond the potential applications, this research also have profound implications for our fundamental understanding of the universe, right?
Absolutely. Think about it. Heavy ion fusion is happening all the time in stars.
Oh, yeah.
Creating the elements that make up everything around us, including ourselves.
That's right.
By studying these collisions in the lab, we're essentially recreating the processes that forged the very fabric of the cosmos.
Wow, that puts things into perspective.
Yeah.
So this research isn't just about creating new elements, it's about understanding like the origins of everything.
Exactly.
It's about connecting the dots between the smallest particles and the grandest cosmic events.
Exactly. It's about understanding the fundamental forces that govern the universe.
Wow.
The same forces that were at play in the Big Bang. This new model, with its incredible accuracy and its ability to capture the complex dynamics of these collisions, gives us a powerful new tool to probe these mysteries.
It's like we've been given a new lens to view the universe, one that allows us to see things with greater clarity and detail than ever before.
And who knows what we might discover with this new lens? This model could lead to breakthroughs in astrophysics, helping us understand how stars evolve and die, how galaxies form and collide. It could even shed light on the mysteries of dark matter and dark energy. The possibilities are endless.
This is truly groundbreaking stuff. I'm so excited to see where this research leads and what other secrets of the universe it helps us unlock.
Me too.
I feel like we've only just scratched the surface of this topic, but unfortunately we've reached the end of our deep dive for today.
It's been a fascinating journey, and remember, this is just the beginning. Science is constantly evolving.
Right.
And who knows what incredible discoveries await us in the future.
If this deep dive has taught us anything, it's that the universe is full of wonders.
And the more we learn, the more amazing it becomes. Thanks for joining us on this incredible adventure, and keep exploring.